Okay, I want to get my mug up here in the corner for a second on this one. All right, so I'm having trouble getting you all to view these things before class. All right, kind of not doing this shit for my health. So, but I don't want to stop doing it because those that are taking advantage of it, you know, I hope it's helping. But anyway, the first thing I wanted to explain about chapter 22, because students were doing 3D, you get electricity and magnetism together. You put them together. You've got this 3D situation here. So, and when we talk about the normal, I talked about this in class on Friday. I didn't talk about it today, but here's a slinky. Okay, now then. It's in the plane of the paper. This pen is now coming straight at you, and it is to this coil. All right. So when the coil rotates, okay. So when the coil rotates like this, it is during this rotation when it went from here to here, it had a change in flux. All right. During that time, the flux was changing because the norm. Here we go. I've got a magnetic field going into the page like this. All right, magnetic field going into the page like this. Boom. So, right now, the magnetic field is anti-parallel. Well, I should have had it coming out. Okay, well, we can have this going down. All right, we can have the normal pointing down. Okay, now it's parallel to, well, let's do it this way. It is what we'd call anti-parallel. It doesn't matter. It's got, okay, it has no flux. What the word, it has no flux. Here it is, no flux. Now when we rotate it during the time the flux is changing, boom. Now and if we stop here, now it's still, even though it's perpendicular, that's when it's got the maximum flux when the normal is perpendicular to the magnetic field, and then it goes back through, boom, from flux back to zero flux. It goes from zero flux to a maximum flux, and the normal is what from the surface of the coil. Okay, so what does flux equal? Well, flux is equal to this. Magnetic flux, this guy. Starting to look like Gauss's law a little bit, right? Kind of, sort of. Is equal to negative, and that's just for the polarity, the north-south, the changing of the changing voltage, because it's going to be an AC circuit going back and forth. All right, times the B times the magnetic field times the area of the magnetic field, MBA, times the cosine that the normal, here's my normal, that the normal makes with the magnetic field. So here's my normal. When it's pointing down, it's completely parallel to it. Now it's anti-parallel. Still the same. It's still a maximum. It's just the voltage in this. And remember, electrons don't care if the voltage is positive or negative. It's going to push them. So there we go. So as my flux changes, as NBA cosine of theta changes over time, in other words, as I change the thing, usually what we do is changing the area of a coil of wire is kind of hard. So what we do most of the time is rotate the sucker. All right? Is we rotate it. So the change in flux, or the change in time, is equal to this. And guess what? That gives us an average EMF. That's the entire chapter in a nutshell. All right, and then everything else is just a variation. Okay, how we use this rotating coil, or some of the problems they might stretch, bounce it back. stretch it, bounce it back, you know, those kinds of things. But main thing is you got a coil of wire. N is the number of coils. B is the magnetic field it's in. A is the area of the wire, so this would be a pi r squared type thing. And the cosine, the angle again, the angle is the most important thing. It is where students have a hard time, is because they want to have it the angle of the plane of the coil, but it's actually the normal to the plane of the coil. And the normal is that 90-degree angle like this. Whoops. See how to the plane of the wire? That's what we do. We wrote a big idea. Now I'm going to show you some PhET simulations of it.